So my thing cut. I have to start the entire lecture again. So let me just lower the brightness. So in this lecture, my goal for you guys is to introduce you guys to the most advanced theory in LOSC at the moment. So as of the recording of this video, it's still ongoing, the research is still ongoing. If you guys want to collaborate with me, just simply email me. But nonetheless, let's start this thing. So what I want to lead to is straight here. So right now, the entirety of our physics, in bullshit physics or mathematics, is currently governed by two main physical theories. That is rigid dynamics and cathode gravity. And these are they correspond to their own real-life physical theory. So rigid dynamics corresponds to quantum mechanics, and cathode gravity corresponds to general relativity. Now, because quantum mechanics and general relativity on their own cannot be reconciled, so there is no direct correspondence or fundamental theory that is proven at the moment that unifies quantum mechanics and gravity. That would mean that rigid dynamics and cathode gravity have no fundamental theory as well that unites them. We are basing concepts off of real-life physics, are we not? And because we're doing that, we lend ourselves to certain inconsistencies in these theories that prevent us from unifying them into one grand unified physical theory. Now, there are many attempts at this in trying to unify quantum mechanics and gravity. And gravity essentially. Because the thing is, right now we have the standard model. The standard model gives us particles and their interactions. However, the problem is gravity. Because we have no quantum for gravity. There is no graviton that we have detected just yet. So, this is all just theory at the moment. Okay. Now, there are many ways to unify quantum mechanics and gravity, and equivalently, rigid dynamics and cathode gravity. So some of those is, of course, string theory. There is the loop quantum gravity and many others. M theory, there's a whole universe of physical theory, advanced physical theories that tries to unify quantum mechanics and gravity, and it's the swamp, essentially. It's called the swamp, right? So what I want to lead to is string theory, and most notably MILFS. So, what does MILFS have to do with this? So, first let's define what a MILF is, right? So, you guys already noticed from Professor Lando's video, MILFs are moms I'd like to fuck. But what I want to teach to you guys today is a certain classification of these types of MILFs. So, we can break down MILFs into two main types. So, I will call the first type the kappa type. So, kappa type. And the second type is that I-type MILF. And this is really just terminology. You can name these guys two different names, but they're still fundamentally what I would call the thick MILF. Two C's, okay, two C's. Thick MILF. And the thin MILF. T-H-I-N. And these types of MILFs correspond to a certain, so any type of MILF you can think of that falls under these two categories corresponds to their own particle in the standard model. So each MILF you can think of that falls under the I-type MILF can correspond to a certain fermion. Corresponds to a fermion. So if I have a MILF M, and I'd say it falls under the I-type, then it has a corresponding fermion associated to it. So for example, let's say that this MILF that I drew on the board corresponds to the quark, so to an up quark, essentially. Right? Let's just say that it corresponds to it. So that's my point. Each or every MILF you can think of that falls under the kappa type or the I type sexy or whatever. The point is they're associated to the Higgs boson, essentially. Okay, so that's what I want to tell you guys right now. So MILFs can be classified into two different types, the kappa and the I-type MILF. And each of these types of MILFs correspond to either bosons or fermions. And because each type of MILF corresponds to a boson or a fermion, that would mean that they give rise to everything. So each interaction or whatever MILFs essentially generate them. So for example, if I have a certain MILF M that corresponds to, let's say, a quark, so I have this one over here, so let's say quark and up quark, and I have another MILF, let's say, that corresponds to, let's say M1 and M2, that corresponds to a Higgs field, so an H field, or Higgs mechanism. So what that happens is that if M1 interacts with M2, we generate mass. Or what happens is that the interaction leads to the generation the generation of mass within a catboid. So within an astronomical catboid, or a quantum mechanical femboy system. So that's what happens if these two types of MILFs interact. So, of course, you guys can formulate all of this through the standard model Lagrangian and study the physics under those. But what I want to focus on today is string theory. So, you can use quantum field theory to study these two types of MILFs, but what I want to posit is a much more fundamental theory that changes everything, or that formulates everything in a very elegant manner, and could possibly be this generation's breakthrough. So, using this theory, string theory, we can possibly reconcile rigid dynamics with catboid gravity. So, what I want to reach to you guys right now, so what I want you guys to learn at the end of this lecture is that certain types of strings generate your MILFs M. Just like how strings, so real physical, I won't say real, but rather sort of real, formulated in real life or in real life physics type of strings generate the particles that you know. So each of these strings lend to certain particles in the standard model. Just like that, strings lend themselves to certain MILFs, and then the MILFs lend to certain physical systems, so macro systems. Quote unquote macro systems that aren't subatomic in nature. So, there's that. So, let's study these strings. So, the first thing that we want to study about when it comes to strings that generate MILFs is the action. So in the last video, wherein I discussed the action in catboid gravity, I discussed or I emphasized how important the action was, because that tells us everything we need to know about a physical system. So we can know everything that we need to know about a certain particle traveling through a space-time if we examine its action, which tells us everything about the energy and whatnot. So, when we want to study strings, the most important thing that we want to discuss is their action. And we're going to focus on the most basic form of string theory at the moment, and that is bosonic string theory. So, bosonic string theory. I want to focus on this one for this lecture. Okay? And there are two main actions that I want to discuss, or three main actions I want to discuss today, and that is the Nabu-Goto action, the Polyakov action, and the Liouville this Namagoto action is your introduction to this concept of strings, and the Polyakov action and the Liouville action are sort of the real-life equivalents or the more correct forms of the Namagoto action. So actually the Polyakov action and the Liouville action works together to study. So we use it to study excitations or fluctuations on strings. So likewise, we would study it and then how it would, what are the dynamics essentially when they generate a certain MILF and a certain space-time, right? So there's that. So I want to consider first a parameter space. So let's first consider a parameter space which is sigma tau or tau sigma. Tau sigma. Tau sigma. So these are just parameters. They are not physical parameters just yet. They are just parameters. And I consider a function. So this is a plane, right? I will consider a function x mu mu of t tau sigma, x of mu tau sigma, that takes each of these points to a certain higher dimensional space, which is essentially the surface of our world sheet. So, right, we have a particle, and then its corresponding world line parameterized by a certain function lambda. So now, because we're considering strings, which are one-dimensional objects, the path that they trace throughout space is fundamentally two-dimensional in nature. And thus, we would have each coordinate on the surface of our world sheet, which the term was coined by Leonard Susskind. Bless his heart. So each of these coordinates is an x mu of tau sigma. So it's a world sheet. So a string traveling through space-time. So each geodesic, originally one-dimensional in form, is now two-dimensional in form when we're talking about strings. So it can either be this closed string or it can be an open string, and then it would still be two-dimensional in nature. Each of these points is still an x mu tau sigma. And it's all taken from some parameter space down below, doesn't matter where. And that's that. So this mu ranges from 0 to 3, just like our previous use of these types of indices. And what we're really considering is a tuple, a four-tuple of these functions that generate the world sheet of our particle. So if you want to describe your particle or your string that generates our MILFs, it would be described through this kind of mathematical object. So, next, I'm going to introduce some notation. So, bear with me for a second because this notation is a bit confusing, but we denote this eta mu mu to be the metric, so this is the metric on the d plus 1 dimensional space-time that our string lives in. So, the metric on d plus 1 space-time. So, a while ago, we considered 4 dimensions, so a 4-tuple. So that would mean we would consider this metric would be on a 3-dimensional space-time, essentially. So we're talking about the 5-dimensional space-time, like that. 5-dimensional space-time. So, where's that? So, a while ago we considered x mu mu. So, in the original text, the tuple is a d-tuple, right? So it would be from x0 tau mu up to x to the d of tau mu, and I can find that this simply d equals 4. So this eta mu mu is the metric on the space-time this particle lives in. It's not necessarily the metric on the parameter space, but rather the surrounding or the ambient space-time. Okay, so we define the contraction GAB. So this contraction is still a matrix to be the sum eta mu mu dx mu So we're essentially summing over 0, 1, AB, and we take this into consideration essentially when we plug in our index. So that's another thing. And this GAB is called the induced metric on the world sheet. So this determines the actual geometry on the surface of our world sheet, or how it moves through space-time. So while this one determines the shape of our world sheet, this determines the dynamics of the world sheet, essentially. So this is essentially our equation of motion. So the area of the world sheet would then be something called A. The area is then given by, so dA is equal to, get this right, d squared sigma, big sigma, square root of negative g, where this d squared sigma is some shorthand notation for d sigma d tau. And this g, without an AB, is simply the determinant of my GAB over here. Because this is still a matrix, this is still a tensor, right? So G is the determinant of GAB. So then, if I denote this over here, so I'm going to make some more notation. So x dot is defined to be my dx mu by d tau, and my x prime, give me my dx, is this numerical? Just dx, my bad. So dx by d sigma. So we're taking the derivative of the entire vector, essentially. So if I use this notation, then I can rewrite my GAB into the following form. So GAB is then this matrix over here. So it's x dot squared. So x dot x prime dot x dot, and x prime squared. And the corresponding determinants of G would then be x dot squared, x prime squared, minus x dot x prime squared. And I want to note that each of these dots is some contraction. So x dot y, so you can substitute y for x prime and x for x dot, is essentially equal to my eta mu x mu y mu. So it's a contraction, recall, or remember this is a contraction. Okay? So it's not essentially a matrix inside our action, but rather it would be some function, some singular function that we integrate, or some singular function of sigma and tau that we integrate. So keeping in mind all this notation, our action works out to be the following. So the Nambu-Goto action is the following. So the Nambu-Goto action, S, is the negative TO over C times the integral of dA. And plugging dA into the equation gives me the following form. So S is negative TO over C, integral of d squared sigma times the square root of negative g. And before I go further in expanding it, this TO is the tension on the string, and C is the speed of light. And the speed of light and each of these guys ensure that some unit consistency is observed when we are discussing these certain concepts or this action. So the units check out. So these guys ensure that. And more often than not, we will employ the natural units where C is equal to C is equal to 1. Same as h bar, same as the Newtonian gravitational constant. We set those equal to 1. So the fully expanded form will be the following. So the action on your particle is TO over C, the integral of tau times the square root of, so since it's negative, I just switch my determinant, right? So the terms of my determinant, so it will give me, let's see, is it correct? Okay, yeah. So that would be x dot x prime squared minus x squared, x dot squared times x prime squared. And still keep in mind the contractions, because it would still depend on the metric on my space-time eta. So all of this still depends on the metric. So although you won't get some matrix equations or equation containing a matrix, you guys will have a certain system of these actions, this Nambu-Goto action. So now that I've given you the Nambu-Goto action, I will tell you that this is wrong. It's only good as an introductory action, and I think I'll give you guys an exercise on this later. But this is not the correct form. There are still some inconsistencies, or there's still a more accurate version of this that we can actually use in quantum mechanical computations. And that corrected form, the corrected form is given by the Polyakov action. And to consider the Polyakov action, we consider the conjugate momentum field. So the conjugate momentum field, capital P, essentially negative T over the square root of negative G times my differential value, so it's in a different form, x prime times x dot x prime minus x dot x prime squared. So I introduce this notation, or this concept, and now we can define the Polyakov action. So the Polyakov action is then the following, and this is the actual real thing that you would want to use if we want to find the correct quantum theory. So the S is T over 2. D is still the tension on the string. Okay? So T over 2 times D squared sigma times the square root of negative G times, so this is a bit more complicated, so G, A, B, so we raise the index, remember raise your indices, and then take the derivatives of G mu. So G mu is something else, so I'll define that later. Dx mu by dya dx mu by dyb. So this is the Polyakov action. Okay, so there's that. And before I go further into the Liouville action, first define the Hamiltonian. So I said I would talk about the Hamiltonian. It's essentially the sum of the kinetic energy and the potential energy. You guys should know that already by now. And using this momentum field over here, we would say that the Hamiltonian of our system is then the integral with respect to sigma times lambda times p squared plus t squared x prime squared plus rho p times x prime. Where in this rho and this lambda over here are your appropriate Lagrange multipliers. So the necessary Lagrange multipliers is what rho and the lambda is in my equation. So this is the Polyakov action. This is the correct form. We raise the index and then we replace the index with a mu and then contract essentially. And if I'm not mistaken, this is essentially something else. So G mu is actually the metric on the 2D space, which I will say later. This G mu could be sort of the ambient, still the metric on the ambient space, or it could be the metric on the on our parameter space. However, that's what really it is. So we define this later. So now we're going to talk about the Liouville action. still on strings. However, combining our use of the Polyakov action and the Liouville action, we can actually study the dynamics of certain fluctuations on the strings. So you consider a field phi. So the action over the field phi is then 1/4 pi times the integral of d squared x times the square root of g times g mu nu, raise the index, don't forget, d mu phi plus q, still recording? Yep, still recording. Q r phi plus lambda prime e, so I'll just write it as x of 2b phi. A lot of constants here. So this lambda prime is the cosmological constant, or it's often called the cosmological constant. My phi, or the field that I'm investigating this on, is called the Liouville field. It's still, this g mu, as I said, was still the metric on my 2D space. And r over here is the Ricci scalar of my g mu. So it's the Ricci scalar of my g mu. And some more constants over here that I don't really want to go bother explaining. So there's that. So if you guys want to start off with a very basic geometric dynamics of a string that generates our MILFs, without any consideration for real life constants or whatever, or real life quantum or the quantum theory, then you want to start off with the Navier-Goto action. And if you want a more better quantum theory, then you will use the Polyakov action. And if you want to study fluctuations on those strings, you want to use the Polyakov action along with the Liouville action. So there's that. So in summary, just to recap before I end this lecture, everything that we have in cat-point gravity and in Bridget dynamics is generated by certain types of MILFs, the I-type MILF and the kappa-type MILF. And the strings that give rise to these MILFs essentially can be studied using these actions. So there's that, actions. These certain actions are what we will use to study those types of strings, essentially. And so that's really the aim for this lecture. And along with that thing, the original lecture was actually quite long. The introduction was quite long, but now I just wanted to get it over with. So that's really it for this lecture. I don't know when I'm going to upload this along with my cat-point gravity lecture. I don't know if that lecture that I'm going to record or that I'm going to upload before this one is going to be the last one. We're not really sure where this year is going to go next because it's rather complex, and I'm really only I'm a one-person department here. So in advanced studies at LOS, I'm the only researcher, and subsequently I'm the only professor. Again, we're accepting applications, right? I really want to make this a team effort, okay? Because I can't do this alone. And I'm pretty sure Professor Nando has tried the same tactic. He's tried recruiting professors to help him with lecturing. But because we are dealing with much more advanced and esoteric physics or mathematics, then I really can't do this alone. So any applications would be really helpful. And especially if you are a seasoned physicist or mathematician, joining LOSU would be a really, really big help for me. Okay, and if you guys join, or if you guys are recruited into LOSU as a professor or an instructor, you guys can create your own channel and then lecture there, essentially, or send me the lectures and I will upload it here. So that's really it for this lecture, and I guess I'll see you guys in the next one.